Approximation algorithms. Following our encounter with NP-completeness and the idea of computational intractability, in general, we've been dealing with a fundamental question. How should we design algorithms for problems where polynomial time is probably an unattainable goal? In this chapter, we focus on a new thing related to this question: approximation algorithms which run in polynomial time and find solutions that are guaranteed to be close to optimal. There are two key words to notice in this definition: close and guaranteed. We will not be seeking the optimal solution, and as a result, it becomes feasible to aim for a polynomial running time. At the same time, we will be interested in proving that our algorithms find solutions that are guaranteed to be close to the optimum. There is something inherently tricky in trying to do this. In order to prove an approximation guarantee, we need to compare our solution with and hence reason about an optimal solution that is computationally very hard to find. This difficulty will be a recurring issue in the analysis of the algorithms in this chapter. We will consider 4 general techniques for designing approximation algorithms. We start with the greedy algorithms analogous to the kind of algorithms we developed in Chapter 4. These algorithms will be simple and fast, as in Chapter 4, with the challenge being to find a greedy rule that leads to solutions provably close to optimal. The second general approach we pursue is the pricing method. This approach is motivated by an economic perspective. We will consider a price one has to pay to enforce each constraint of the problem. For example, in a graph problem, we can think of the nodes or edges of the graph sharing the cost of the solution in some equitable way. The pricing method is often referred to as the primordial technique, a term inherited from the study of linear programming, which can also be used to motivate this approach. Our presentation of the pricing method here will not assume familiarity with linear programming. We will introduce linear programming through our third technique in this chapter, linear programming and routing, in which one exploits the relationship between the computational feasibility of linear programming and the expressive power of its more difficult cousin, integer programming. Finally, we will describe a technique that can lead to extremely good approximations using dynamic programming on a rounded version of the input. 11.1 Greedy Algorithms and Bounds on the Optimal, a load balancing problem. As our first topic in this chapter, we consider a fundamental load balancing problem that arises when multiple servers need to process a set of jobs or requests. We focus on a basic version of the problem in which all servers are identical and each can be used to serve any of the requests. This simple problem is useful for illustrating some of the basic issues that one needs to deal with in designing and analyzing approximation algorithms, particularly the task of comparing an approximation solution with an optimal solution that we cannot compute efficiently. Moreover, we will see that the general issue of load balancing is a problem with many facets, and we will explore some of these in later sections. The problem. We formulated the load balancing problem as follows. We are given a set of m machines, m1, m2, m3 until mn, and a set of n jobs. Each job j has a processing time tj. We seek to assign each job to one of the machines so that the loads placed on all machines are as balanced as possible. More concretely, in any assignment of jobs to machines, we can let A of I denote the set of jobs assigned to machine mi. Under this assignment, machine mi needs to work for a total time of ti equals to capital Ti equals to the summations of little tj, summing for all index j, which is in A of I. And we declare this to be the load on machine mi. We seek to minimize a quantity known as the makespan It is simply the maximum load on any machine, t equals to the maxima of ti, where the maxima is taken among all possible index I. Although we will not prove this, the scheduling problem of finding an assignment of minimum make span is NP hard. Designing the algorithm. We first consider a very simple greedy algorithm for the problem. The algorithm makes one pass through the jobs in any order. When it comes to job j, it assigns j to the machine whose load is smallest so far. Greedy balance. Start with no jobs assigned. Set ti equals to 0 and a of I equals to empty. Set for all machine mi. For j equals to 1, 2, 3 until n, let mi be a machine that achieves the minima min tk, where the minima is taken among all possible k. Assign job j to machine mi. Set a of I equals to a of I union the singleton set j. Then we set tj equals to ti equals to ti plus tj. So for example, in figure 11.1 shows the result of running this greedy algorithm on a sequence of 6 jobs with the sizes 2, 3, 4, 6, 2, 2. The resulting make span is 8. The height of the job on the first machine. Note that this is not the optimal solution. Had the jobs arrived in different order, so that the algorithm saw the sequence of sizes 6, 4, 3, 2, 2, 2, then it would have produced an allocation with a make span of 7. Analyzing the algorithm. Let t denote the make span of the running assignment. We want to show that t is not much larger than the minimum possible make span t star. Of course, in trying to do this, we immediately encounter the basic problem mentioned above. We need to compare our solution to the optimal value t star, even though we don't know what this value is and have no hope of computing it. For the analysis, therefore, we will need a lower bound on the optimal, a quantity with the guarantee that no matter how good the optimal is, it cannot be less than this bound. There are many possible lower bounds on the optimal. One idea for a lower bound is based on considering the total processing time, the summations of tj summing for all index j. One of the m machines must do at least a 1 over m fraction of the total work, and so we have the following. 11.1. The optimal make span is at least t star, which is greater than or equals to 1 over m times the summations of tj summing for all index j. There is a particular kind of case in which this lower bound is much too weak to be useful. Suppose that we have one job that is extremely long relative to the sum of all processing times. In a sufficiently extreme version of this, the optimal solution will place this job on a machine by itself, and it will be the last one to finish. In such a case, our greedy algorithm would actually produce the optimal solution, but the lower bound in 11.1 isn't strong enough to establish this. This suggests the following additional lower bound on t star, that is 11.2. The optimum make span is at least t star, which is greater than or equals to the maxima of tj, where the maxima is taken among all possible j index. Now we are ready to evaluate the assignment obtained by our greedy algorithm. 11.3. Algorithm greedy balance produces an assignment of jobs to machines with a make span t, which is less than or equals to 2t star. Proof. Here is the overall plan for the proof. In analyzing an approximation algorithm, one compares the solution obtained to what one knows about the optimal. In this case, our lower bounds 11.1 and 11.2. We consider a machine Mi that attains the maximum load T in our assignment, and we ask, what was the last job J to be placed on Mi? If Tj is not too large relative to most of other jobs, then we are not too far above the lower bound 11.1. And if Tj is a very large job, then we can use 11.2. Figure 11.2 shows the structure of this argument. Here is how we can make this precise. When we assign job J to Mi, the machine Mi had the smallest load of any machine. This is the key property of our greedy algorithm. Its load just before this assignment was capital Ti minus small tj. And since this was the smallest load at the moment, it follows that every machine had load at least capital Ti minus small tj. Thus, adding up the loads of all machines, we have the summations of tk, summing for all index k which is greater than or equals to m times capital Ti minus little tj, or equivalently, that is capital Ti minus little tj is less than or equals to 1 over m times the summations of tk, summing for all k, where the tk is for capital T. But the value, the summations of tk summing for all k, is just the total load of all the jobs, the summing of tj summing for all j, since every job is assigned to exactly one machine. And so the quantity on the right-hand side of this inequality is exactly our lower bound on the optimal value from 11.1, thus tj, capital Ti minus small tj is less than or equals to t star. Now we account for the remaining part of the load on Mi, which is just the final job J. Here we simply use the other lower bound we have 11.2, which says that Tj is less than or equals to T star. Adding up these two inequalities, we see that Ti is equals to Ti minus Tj plus Tj, which is less than or equals to 2T star. So since our make span T is equals to Ti, this is the result we want. It is not hard to give an example, which the solution is indeed close to a factor of 2 away from optimal. Suppose we have m machines and n equals to m times m minus 1 plus 1 jobs. The first m times m minus 1, which is equals to m minus 1 jobs, each required time tj equals to 1. The last job is much larger. It requires time tn equals to n. What does our greedy algorithm do with this sequence of jobs? It evenly balances the first m-1 jobs, and then has to add the giant job n to one of them. The resulting making span is t equals to 2m minus 1. What does the optimal solution look like in this example? It assigns the large job to one of the machines, say M1, and evenly spreading the remaining jobs over the other m-1 machines. This results in a make span of m. Thus, the ratio between the greedy algorithm's solution and the optimal solution is 2m minus 1, then divided by m, which is equals to 2 minus 1 over m, which is close to a factor of 2 when m is large. See figure 11.3 for a picture of this with m equals to 4. One has to admire the perversity of the construction, which misleads the greedy algorithm into perfectly balancing everything, only to mess everything up with the final giant item. In fact, with a little care, one can improve the analysis of 11.3 to show that the greedy algorithm with m machines is exactly within exactly this factor over 2 minus 1 over m on every instance. The example above is really as bad as possible. Extensions or an improved approximation algorithm. Now let's think about how we might develop a better approximation algorithm. In other words, one for which we are always guaranteed to be within a factor strictly smaller than 2 away from the optimal. To do this, it helps to think about the worst case for our current approximation algorithm. Our earlier bad example had the following flavor. We spread everything out very evenly across the machines, and then one last giant unfortunate job arrived. Intuitively, it looks like it would help to get the largest jobs arranged nicely first, with the idea that later small jobs can only do so much damage. And in fact, this idea does lead to a measurable improvement. Thus, we now analyze the variant of the greedy algorithm that first sorts the jobs in decreasing order of processing time and then proceeds as before. We will prove that the resulting assignment has a make span that is at most 1.5 times the optimal. Sorted balance. Start out with no jobs assigned. Set Tj, capital Ti, equals to 0, and A of I is empty set for all machines, Mi. Sort jobs in decreasing order of processing time Tj, little tj. Now we assume that T1 is greater than equals to T2, which is greater than equals to T3, and so on, which is greater than equals to Tn. Then we enter for loop for j starting from 1 until n. Let Mi be the machine that achieves the minima make span currently, that is the mean of Tk, where the minima is taken among possible k. Assign job j to machine Mi. Then we set A of I equals to A of I union j, including job j into machine Mi. Then we set Ti equals to Ti plus little tj. We increase the make span of machine Ti. The improvement comes from the following observation. If we have fewer than m jobs, then the greedy solution will clearly be optimal, since it puts each job on its own machine. And if we do have more than m jobs, then we can use the following further lower bound on the optimal. 11.4. If there are more than m jobs, then T star is greater than equals to 2 times Tm plus 1. Proof. Consider only the first m plus 1 jobs in the sorted order. They each take at least Tm plus 1 time. There are m plus 1 jobs and only m machines, so there must be a machine that gets assigned 2 of these jobs. This machine will have a processing time at least 2 times Tm plus 1. 11.1. Algorithm sorted balance produces an assignment of jobs to machines with the make span t, which is less than or equals to 2/3 times T star. Proof. The proof will be very similar to the analysis of the previous algorithm. As before, we will consider a machine Mi that has the maximum load. If Mi only holds a single job, then the schedule is optimal. So let's assume that machine Mi has at least 2 jobs, and let Tj be the last job assigned to the machine. Note that j is greater than or equals to m plus 1, since the algorithm will assign the first m jobs to m distinct machines. Thus, Tj is less than or equals to Tm plus 1, which is less than or equals to 1/2 times T star, where the second inequality is 11.4. We now proceed as in the proof of 11.3 with the following single change. At the end of that proof, we had inequalities. Capital Ti minus little tj, which is less than or equals to capital T star, and small tj is less than or equals to T star, capital T star, and we added them up to get the factor of 2. But in our case here, the second of these inequalities is, in fact, Tj, which is less than or equals to 1/2 times T star. So adding the two inequalities gives us the bound Ti which is less than or equals to 2/3 times t star.